Hello and welcome back. Today we'll be doing question 2 from the 2013 STEP Paper 1. So, let's get started. In this question, this symbol over here, which is the floor of x, denotes the greatest integer that is less than or equal to x, so that floor 2.9 is equal to 2, which is equal to the floor of 2, and the floor of negative 1.5 is equal to negative 2. The function f is defined for x not 0 by f of x is equal to floor of x over x. Part 1. Sketch the graph of y equals f of x for negative 3 less than or equal to x less than or equal to 3, with x not 0. Part 2. By considering the line y equals 7/12 on your graph or otherwise, solve the equation f of x is equal to 7/12. Solve also the equations f of x is equal to 17/24 and f of x equals 4/3. Part 3. Find the largest root of the equation f of x is equal to 9/10. Give necessary and sufficient conditions in the form of inequalities for the equation f of x is equal to c to have exactly n roots, where n is greater than or equal to 1. Pause the video to have a think, and once you're ready, restart to see if you were correct. So, let's get started. Firstly, I put an empty circle at the origin, since the curve is not defined at x is equal to 0. Now, I'd look at the region between 0 and 1. Here, the floor of x is always equal to 0, and therefore the value of the graph will always be 0. Now, I'll look at the region between 1 and 2. Here, the floor of x is always 1, and therefore we have 1 over x. Similarly, between 2 and 3, we have 2 over x. Now, if we look at the negative side, we'll see that between 0 and negative 1, the floor of x will always be negative 1. Therefore, we have negative 1 over x. Similarly, we'll also have negative 2 over x between negative 1 and negative 2, and also negative 3 over x between negative 2 and negative 3. Now, this here is my attempt at drawing the graph, and down below is Desmos's attempt at drawing the graph. Notice, though, that Desmos has not put in any solid or unfilled circles. However, these are very much required, as the graph does a bit of jumping, and you must notice that certain points are defined, whereas certain points are not. For example, at the point x equals 2, the floor of x is equal to 2, and therefore we have 2 over 2, which is 1, and not 1/2. Now, we can move on to part 2. Here, we'll draw in the line y equals 7/12. We'll notice that it's between 1/2 and 2/3, and therefore it will lie between the endpoints of the 1 over x section and the 2 over x section. This means, of course, that the line has only one solution. We can solve it by equating 7/12 to 1 over x to get x equals 12/7. Similarly, 17/24 is between 2/3 and 3/4, and drawing this on the graph gives us two solutions. We now need to set 17/24 to both 1 over x and 2 over x, and this should give us 24/17 and 48/17 as the two possible answers. Now we need to look at 4/3. If we draw the graph of 4/3, we'll notice that at negative 3, it seems to intersect the graph that Desmos gave us. However, if you remember my graph up here, at negative 3, the value of the graph is equal to 1 and not 4/3. Therefore, this graph does not actually intersect our line at x equals negative 3. Therefore, we only need to equate 4/3 to negative 1 over x, negative 2 over x, and negative 3 over x. This gives us x is equal to negative 9/4, negative 3/2, and negative 3/4. Now we'll move on to part 3. Here we've got 9 over 10 is equal to k over x. If we plot y equals 9 over 10 on the Desmos graph, then it will seem to intersect our graph f of x at x equals 10. However, remember that at x equals 10, the floor of x is also equal to 10, and the value of the graph is equal to 1, not 0.9. Therefore, the largest root is actually the intersection with the 8 over x section of the graph. We therefore have 9 over 10 equals 8 over x, and x is therefore equal to 80 over 9. Now, we'll move on to the very last part, which is unnumbered. Notice, though, that we can achieve any number of roots with 0 less than c less than or equal to 1. If we have the value of c going across at, for example, 0.1, then this will have no roots because it will not intersect anything. However, once we move to having c between 1/2 and 2/3, then f of x equals c will have one root because it passes through the graph once. Similarly, the number of roots will increase as we increase c towards 1, and at c equals 1, f of x equals c will have infinite roots. Now, we'll look at the lower bounds of these graph sections. Here, we'll see that this point has a value of 1/2, this point is at 2/3, and this point over here, which is off the graph, is 3/4. This all seems to be of the form n over n plus 1, and therefore we can say that a sufficient condition for f of x equals c to have exactly n solutions is that n over n plus 1 is less than c is less than or equal to n plus 1 over n plus 2. Equality can only be achieved on the right-hand inequality sign because the lower end of all of these graph sections cannot be attained by the graph f of x. Now, this statement is sufficient, but is it necessary? If we go back up and we say that the equation has precisely one solution, then we could have the graph going between 1/2 and 2/3, for example, here. However, the value of c could also be greater than or equal to 2, and it would still have precisely one solution. So, the condition is not necessary, despite it being sufficient. Here, you'll notice that the top ends of these graph sections are 4/3, 3/2, 2 over 1, and what would appear to be 1 over 0, but is in reality infinite, because 1 over 0 is undefined. These all seem to be of the form n over n minus 1, and therefore a necessary condition for f of x equals c to have n solutions is the combination of the sufficient conditions for the left-hand side of the graph and the sufficient conditions for the right-hand side of the graph. Therefore, a sufficient condition is that n over n plus 1 is less than c, which is less than or equal to n plus 1 over n plus 2, or n plus 1 over n is less than c, is less than or equal to n over n minus 1. And that's the answer. If you liked our video, please like and subscribe, and we'll see you next time for some more fun maths problems. Thanks for watching, and goodbye.